everyone. Welcome to another episode. I think it's episode 10, yeah, of our
Something
weekly
like that.
something, right? Yeah, I can't believe it's been like this long. So it's about our real-time Gen AI with Java. So let's crack the code. But today we are very happy to have Jonathan Ellis, our founder of DataStax, to join us, and then of course also Cédrick, our leader in one of the engineering teams, and formerly with the DevRel lead. So, and of course Aaron and myself. So yeah. So with that, we want to welcome Jonathan, and today we'll kind of have a chat about vector search.
Delighted to be here. Thanks for having me join you.
Thank you. Yeah.
Yeah, maybe a good start, would be Jonathan, real quick, just for our listeners, tell everyone a little bit about yourself.
Yeah.
So I started DataStax in 2010 to commercialize Apache Cassandra. I led our Cassandra engineering for a few years, and then I kind of got pulled over to the dark side of management. I burned out on that. It doesn't make me happy. Writing code makes me happy. So this year I went back to writing code, and I've led the development of vector search for Cassandra and for DataStax Astra.
Yeah, I can understand that. I also have some role with more and more management until I reached the roof, and I said, no. Bring me back into the cave doing code.
Yes.
Same pattern.
Yeah, I mean, nothing against people. I've known some great engineers who became great managers, but that's not how my mind works. I really enjoyed the part of actually, writing the code and debugging the code and all of that.
Well, I can definitely relate to that too. When I was at Target for several years, and my role there was mostly in a DBA operator kind of a role. And when I first came back to DataStax and then started working with Cédrick, we had our first workshop we were getting ready for, and I had to write a bunch of Java code for it. And I'm like, oh my God, I forgot how awesome this is. It's just been a while.
You're not kidding. So this might not be where we wanted to take the episode, but so first of all, writing code is just awesome. Just from first principles that you're creating something out of nothing, right? Like something that didn't exist, now it does, and that's just the best feeling. But I timed coming back to code really amazingly well, because this is the year of having an AI intern that helps you write code. And I guess the two things that I love about that is, I guess there's three things that I love about it, maybe more. We'll keep going. But the first one is that I can just give the simple projects or the simple boilerplate classes to GPT. And I've gone as far as saying, hey, I need you to write me a thread-safe bit set. And that's the kind of thing that it's in its abilities, but you'll need to go back and forth a little bit to get it correct. Sure. But it can do it. And doing that with GPT is just at least 5 times faster than doing it by hand. Like, can I do that by hand? Sure. Is it fun? Yep. Not really. You're not. It's not particularly novel. It's just you just have to make it work. But the second thing that's really useful for me, and I suspect this is true for other people with ADHD as well. Like when I get to a problem that's especially an unanticipated problem, then that can be really hard for me to just, even though it's not the most difficult problem in the world, just getting the motivation and the energy to push through that can be really difficult. And having GPT there to say, hey, here's what I ran into, what do you suggest? And even though its answers are not always useful, I would say maybe 40% of the time, maybe even less, but just having that to bounce ideas off of is just really, really valuable to in the past, I've lost entire afternoons or entire days to like, oh, I ran into this problem and I I'm going to fart around on, Hacker News for the rest of the day. That has happened.
Right.
So that's really useful for me. And then I said 3. What was the third one going to be? The third one is Code Interpreter, or have they changed the name to Advanced Data Analysis or something? But that's super useful for doing these kind of one-off Python tools. Like I've had it write tools to do analysis on the Git history for me, or visualizing I've printed out the stages of the graph that my index is represented by, printed out the stages as it was constructed, and I told Code Interpreter, visualize this for me. So that's just an entire another category of it's a little bit the same category of the first, where you're giving an intern projects to do, but it's different because this is kind of front end code, and that's not my thing. So having something that's familiar at a basic level with all the libraries in the world, more or less, is just really useful.
Totally. Yeah, and that's how I feel about ChatGPT, right? If we put it to use, it's really big help. But the thing is, there are no guardrails, so it can be unintentional. People can be using it for something else that's not shouldn't be used. But to put it to good use, definitely, I think it's good thing. So.
Yeah, so not going too deep, but me, I like to have elegant code, so I can spend a lot of time doing generics and using the latest object. And the more you're doing that, the more fluent your API can become, and you see your method getting smaller and smaller. And when I got to the point where it's almost one line for each method and everything's work as we expect, I say, hey, GPT, optimize that. And phew, now it's 2 lines and say, oh, hell. It's better than me now.
So bringing us back to our core subject here. So now let's move on to JVector. Jonathan, that's kind of what we brought you here to talk a little about. So
it's my favorite subject in the world.
Outstanding. The initial implementation, I was going to say, of Vector on AstraDB was done with Lucene HNSW, right?
Yeah. So more specifically, it was a fork of Lucene where I took the HNSW code and I made it concurrent. So not only concurrent, but I made it non-blocking, so you can have multiple threads building the index at the same time without blocking each other.
Nice.
So yeah, that was a good starting point. Having the Lucene implementation saved us a ton of time, not just from we're going to use this out of the box, but we did some pretty heavy surgery on it. But just having that, Michael, I forget his last name, but Michael, who wrote most of the HNSW implementation there, had a really comprehensive test suite, and that was super useful in getting the bugs out of the concurrent implementation as well. So yeah, that's what we did our open beta on, and that's what we GA'd on as well.
Wow, wonderful. Yeah.
Excellent.
But it's not good enough.
That's right. Yeah.
Yeah, right. So the challenge with HNSW, and well, let's back up. The good things about HNSW, and this is why everybody starts with HNSW, right? So if you look at the general purpose vector search databases out there, Weaviate uses HNSW, Quadrant uses HNSW, Elastic and Solar and OpenSearch all use Lucene's HNSW. Everybody uses that for 2 reasons. One is that you can build it incrementally. So a bunch of the alternatives, if you're the main alternative to graph-based, so HNSW is part of a larger category of approximate nearest neighbor algorithms that use a graph-based structure. And with the graph-based family, you can build them incrementally without knowing your entire data set ahead of time. The main alternative that people use are variants of, I'm going to partition these vectors somehow, and then when I have a query, I'll select the partitions that are closest to the query, and then I'll just look in those partitions. So it's an alternative way of reducing the work that you have to do that search. The problem with those is that you do need to know your entire data set ahead of time before you can create accurate partitions. So when you're building a database where you want to, every time someone inserts a row, you want to be able to query that and search and find that vector that they just inserted, the partitioning approaches just aren't a good fit.
Right.
So with the other nice thing about the graph-based family and HNSW in particular is that not only is it fast, but it's also accurate. So if you pick if you pick a default or a close to default configuration from Facebook's Face vector indexing library, for instance, and Face is a great piece of work from Facebook that gives you basically every vector search algorithm that we know of, or every vector indexing algorithm that we know of is implemented in Face. But most of the algorithms there, if you just pick the default parameters and say, okay, index my data, you'll probably get around 50% recall, meaning if I ask for the top 10, 5 of the actual top 10 will be in the 10 results that the approximate nearest neighbor algorithm gives me back. So that's completely acceptable for a lot of use cases, by the way. But 50%, most of us would say that's a failing grade in most contexts. So you want to be able to do better. And HNSW, you can, depending on the data set and how aggressive the index is and so forth, but you can easily get from 75% to 95% pretty repeatedly. And so it's the combination of the speed and the accuracy. It's pretty tough to beat. Now, and that's why so many people use it. So you asked, what was the problem with that? The problem with that is that HNSW, it uses a lot of memory for its index, just because of the nature of the beast. We can go deeper on the algorithms next time. But it uses a lot of memory to build the index, and because it is a graph-based algorithm, what you're doing when you're searching for the nearest neighbors is you're basically doing a breadth-first search. And as you expand a node and say, hey, what edges do you have? What neighboring nodes or what neighboring vectors should I expand my search to? Every time you do that, you need to find out, is my search getting closer to my query? Because that's the goal, is to drill down into the graph until you find the closest ones. So you need to know if I'm actually, if going a specific direction actually gets me closer or not. And doing that computation of, am I getting closer? I'm doing a dot product or a cosine or a Euclidean distance across massive vectors of 1536 dimensions if you're using OpenAI's embeddings, which you probably shouldn't be. But even if you're using a smaller embedding vector like the E5v2 that I usually recommend, that's 384 dimensions. That's still very large.
That's still a lot.
Yeah, compared to like doing a search in a database where you're saying select integers greater than 5. Like that's a really easy comparison by contrast. So you're doing these massive comparisons. And to do that, you need to have the vector in memory, not just the index in memory, but the vector data needs to be in memory as well. And so what we found is, as we started to push the index to the edge of fitting in memory and then beyond that edge, the performance really deteriorates really quickly, which is a little bit surprising coming from a database background, because in the database world, there's definitely a very pronounced Pareto principle where you have 80% of the workload touches 20% of the data. So there's always this hot data, and then there's this colder data that maybe it's not as critical for it to be in RAM. But with the vector search, because of the way the graph is constructed, it's almost completely random. You have almost exactly the same probability touching any given node versus any of the others. And so there's no Pareto principle to save you there. And yeah, once you get outside of what fits in memory, it slows down massively as it's pulling those vectors off of disk while you're doing the search.
Right. So at some point along your journey here, you're working with Lucine's HNSW, and at some point, you get to it, and you're like, I'm going to stop doing surgery on this thing, and I'm just going to create my own implementation. So how did that evolve?
Yeah, so my first choice was to upstream the concurrent index to Lucene. Mm-hmm. I don't say this to throw blame anywhere. But for whatever reasons, none of the Lucene committers were super interested in the new code that I was proposing. So so what I ended up doing, and I really wanted this low-level indexing code to be available outside of Cassandra itself, because I think it's more broadly useful than that. What I want, we talked about a little bit at the beginning of how useful AI is in writing code. What I want is a local copilot. I want a local GPT that can answer questions about my code. Mm-hmm. And right now, those only exist as cloud services. And so, every time I get on an airplane, it's like my productivity gets cut in half, which is kind of a drag. And then there's the whole privacy aspect and all of that other stuff as well. So what I want IntelliJ to be able to index my code and use vector search to pull back the most relevant pieces and send it to Llama 7 billion running on JLlama, all in IntelliJ. That's totally possible today. But until JVector was open source, there was that missing piece of how do we do the vector search in Java? Partly because there isn't a really good embeddable Java vector search library out there, and partly because, hey, open source is great. The Cathedral and the Bazaar, having everyone bring a piece of the puzzle and we collaborate, and the whole is greater than the sum of the parts. All of those reasons, I wanted JVector to have its own home and be as accessible to as many people as possible. So I had a motivation to make this accessible vector search library, and I also had a problem to solve, which is making an index that can be faster than HNSW, especially for larger than memory data sets. And there's a couple options proposed in research, but the one that I think has proved out the most in practice is called DiskANN. So Microsoft Research published a paper, I believe in 2019, about this new algorithm called DiskANN. And then they actually open sourced their implementation. That's available if you search for GitHub DiskANN, you'll find the Microsoft DiskANN implementation in C++.
Oh, wow.
And I believe that is in production in Being. So you can look at the commit history. It's been a very active project up to and including today. That was kind of the tiebreaker versus there are other algorithms that people are proposing and saying, hey, this is going to be even faster. But one of the things when you're implementing a research paper, there's a lot of things that look superficially simple, and then it turns out that there's a bunch of gremlins that the paper authors didn't bother spelling out the solutions for. So the fact that not only is this in production, but that there's an open source code base that I can go dive through if I'm like, oh, okay, how did they actually do this? That was really useful. And in fact, I did do that a few times.
Oh, wow.
I maybe next time we can give some examples of where that was useful. But long story short, went with a DiskANN algorithm, implemented it in JVector. The outcome is that you can do your search without hitting disk at all. and there's an asterisk there, but more the right way to think of it is you're not hitting the disk during the search. The reason that you can do that is that you're compressing the vectors with a lossy compression algorithm called product quantization. So you can kind of think of it as JPEG for vectors. You lose a little bit of fidelity, but it makes it much, 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 much smaller. And so you're performing the search with those compressed vectors, which means not only am I not hitting disk, but performing the comparison instead of doing it against a vector of dimension 384, I'm doing it against a vector of 1/16 of that, which is that 24. So it's a massive difference in speed from that as well. So if you go to the JVector project page, there's a graph there where I benchmark Lucene versus JVector on a larger than memory data set.
Right, I saw that.
And JVector is something like 15 times faster. But if you compare JVector versus Lucene on a smaller than memory data set, it's still like 3 to 5 times faster because you're reducing the computation that you need to do during the search. This is a really good example of you can beat your head against the wall trying to make your code faster and optimizing it super at the low level as much as possible. And maybe I would have been able to get another 10% or so out of HNS-W doing that. But the way you get to 5x, the way you get to 15x is by using a better algorithm. So it's always fun when you get the chance to do that.
It's great.
Really great. Yeah.
So it's not only the algorithm, right? You had to look for the latest innovation in Java to achieve that, or moving.
Yeah, that's true. So I mean, there's room for both. The JVector uses Panama's SIMD optimizations to make the dot product computations faster. And last I checked, it's been a while, but the last time I checked, that was getting us about an 80% performance improvement. So if you run JVector with Java 20 or 21, then you will get the SIMD optimizations. If you run it with Java 11 or anything before 20, you don't get those optimizations, but it will still run. So that's
good to know.
Yeah, that's an incentive to upgrade.
Yeah,
exactly.
Yeah,
and it was for us too, right? Like Astra was not running Java 21 until we came up with the SIMD optimizations in JVector and said, now it's worth your time to upgrade.
Oh, for sure.
Yeah. Interacting a lot with users, I see still people saying, yeah, but I'm using GDK 8. And I think starting this year, so now it's your problem. I will not shoot a foot in my, a bullet in my foot anymore. So yeah, it's really a bare minimum. And, I feel comfortable with 17 now.
Oh, yeah.
Yeah, that is a little bit of a source of frustration. Apache Cassandra was on 8 until recently, and now I believe
that's right.
The minimum is going to be 11 for Cassandra 5.0, which is a big improvement. That's a big improvement over 8. Yeah. But it's still, is it 3 years old at this point? Is it older than that? It feels
11, I think so. Yeah.
The JDK has been making such big improvements with pattern matching, with record classes, with lightweight threads, and you don't get any of those on 11. So upgrade.
Yeah. With that, I'm just curious, talking about JDK, I mean, now that JDK 21 has Project Loom that comes out, or the virtual threads, so would you kind of leverage on virtual threads maybe at some point, like I guess for JVector, or have you thought about it too?
So with JVector, I'm not completely sure how this is going to shake out, but what we're doing right now is we have an interface called Random Access Reader, and it's got half a dozen methods. It's got like a readInt method and a read array events and a read array of floats, and I think a read Boolean. I think that might be it. And the idea is that you can implement those in whatever way fits the rest of your project. So for Cassandra, we have some internal classes that use immapped.io, and we have other classes that implement our own caching on top of direct I/O. And so you can create this random access reader from the JVector interface on top of either one of those. With lightweight. The reason this is relevant for lightweight threads is that now that we have that, it becomes a lot more tractable to build asynchronous I/O into your Java application. So the JDK ships with asynchronous network I/O now. In the Cassandra case and JVector case, we're more concerned about disk I/O, which the JDK does not give us a solution for out of the box. However, there's at least one fairly mature library out there for using Linux's I/O U-ring async I/O interface from Java. And so I think this is the part that I'm not sure about because I haven't written the code yet. But I think that the next step is going to be doing async I/O on top of I/O U-ring, and we'll see whether that makes JVector change its interface or not. We may be able to fit it into the same interface, but it may require changes.
The quest of improvements never ends.
Yep.
Yeah, for sure.
Yeah, and if you haven't taken a look at I/O U-ring in a few years, it's been making almost as much progress as the JDK. It's really a lot. It reminds me of when Cassandra was young. Every new big user pushed it in directions that it hadn't gone before. So when Netflix started using it, we added features that Netflix needed. When Spotify started using it, same story. That's been driven. The Linux kernel is driving in the same way because everybody needs fast asynchronous disk I/O, and it's just been a very practically motivated set of improvements.
Wonderful. I guess we definitely will have to have Jonathan back for another episode or more, right? And we'll go even deeper into JVector.
I'd love to.
Yeah. So display this QR code here. That's the JVector GitHub repo. So folks, please sign up and or not sign up, but like follow.
Check that out. Yep.
And star and follow and watch and do all that you can. This is a great. And then also before we go to, we would like to share this Astra DB free trial.
DB running on JVector now, so on Java 21. So
that's right. Yeah. Okay. So don't forget to sign up for us for our Astra DB. So yeah. So with that, I think there's definitely more stuff to talk about, and I learned so much just within less than 30 minutes, and then this has been amazing. Thank you so much, Jonathan.
Absolutely.
Yeah.
Thanks again for having me.
Thank you, and thanks, Aaron, and thanks, Cédrick. Yeah, too. So
no, Jonathan, he's the guest. Thank you.
Thank you.
All right. Goodbye, everyone.
Bye.